Welcome to episode 2 of the video series on variance of a random variable. So in the previous video, we discussed why variance is important or why variance matters. In this episode, we'll try to fit variance in a bigger picture of statistics. We'll try to look into different statistical moments. And where we knew in the previous video that mean is about where the distribution is located, variance tells us about the spread around the mean of a distribution. Similarly, we have different statistical moments like skewness that tells us about the asymmetry of the distribution, and then we have kurtosis that also tells us about the peak, information about the peak and the heaviness of the tail of a given distribution. So let's dive right in. Before moving or looking into different statistical moments, let's look into this example of Taylor series. So what is Taylor series? Taylor series says that a particular function can be represented as a polynomial, or rather some of its derivatives, or if we just keep on adding or expanding the different higher order degree polynomials, we can probably try to approximate this function, or the more higher order derivatives we include in this summation, the better we'll get the understanding of the local structure of this function. So we know that let's say a polynomial of degree 1 would simply look like a line, a polynomial of degree 2 would look like something like this, a 3 would something like this, and then if we try to add all these together with some weight and let's say some higher order derivatives as well, higher order polynomials as well, we can try to approximate a particular curve. Let's say, for example, in this is a function of sine x. This is sine x. And now if we, let's say, try to just approximate it with 1 degree polynomial, it would simply be a line. And this is, we are approximating it around 0 at x is equal to 0. If we consider a polynomial of degree 3, then we'll probably have something like this. And let's say we picked 11, we'll have something looking like this. And if we have 13, then we'll have a better approximation. And if we just keep on adding more and more terms to it, we'll probably have a better approximation of sine x at 0. So we see that the more higher order derivatives we add, the better we are able to approximate a given function. Now, can we apply the same concepts for probability distributions? Can we represent or approximate any probability distributions in terms of simpler components? So statistical moments, now in this case, statistical moments are the one that can describe the shape and the characteristic of a probability distribution. Now, we can also, I would suggest for this video and as well as for the subsequent topics that we're going to discuss, let's try to expand our understanding of how or what a shape of a distribution would look like. We always try to imagine a distribution would be looking something like this, but this is an easiest way to just start something with. But we can expand our understanding that a distribution can either look something like this or this or this, or even if they are continuous, they can also be discrete probability distributions that can be there. Now, when we expand our understanding that they can be of any shape, we will be able to try to connect the dot a little better, and it will be easier for our understanding of for the rest of the concepts. So now, coming back to the different shapes and characteristics of probability distributions. Now, let's say we have a distribution. We want to define a distribution. We can have maybe define a distribution somewhere here, or somewhere here, or somewhere here. So this is the first thing. The location is given by the mean of the distribution, or the mean also tells us that where a particular distribution can be balanced. So how we can balance a particular distribution at a particular given point. So this is the distribution's center of mass. Similarly, now we can also try to have maybe a distribution that can look something like this, a distribution can look something like this, or a distribution can look something like this. So now this notion of dispersion or spread is given by the term that is variance, that is the average squared spread from the mean. And we are always trying to have it around the mean, if we say so. We first define the location where we want to locate a distribution, and then we try to define the spread around the mean. So this is the data volatility that is given by the variance. Now, if you notice here, we are always trying to have a symmetric, again, easier understanding, a symmetric distribution around the mean. So there could be a case that we can define a distribution that can be asymmetric, something like this. It's asymmetric around the mean. That actually is given by the third moment, that is skewness, that is the direction and the degree of the tail bias. So where the tail is a bit more biased or skewed. Then we can have another shape that can probably look something like this. So let's say if we have a distribution, we have defined the mean somewhere here, and we have a curve that can look either like this, or we can also have a curve that can look something like this. So if you see here, if you notice here, this part of the curve is relatively less heavier than this part of the curve. So now this is given by the fourth moment, that is kurtosis, and this is the concentration of data around the mean. That's fine, that's also skewness, but it's also the likelihood of extreme values or the outliers that could probably be present. And because it's a fourth moment, we raise it to the degree of 4. This term kurtosis is actually much more sensitive than, let's say, variance when we are trying to study the outliers in the distribution. So now using these 4 moments, we can see that we can try to define different shapes and different characteristics of a given distribution. So how can we calculate that? Now let's keep things simple again. If we have a probable normal Gaussian distribution, the mean that is given by mu would probably be given by the expected value of that random variable itself. And if you notice, it's raised to the power of 1. So this is the first statistical moment. So mean gives us the location. So in this case, it would be somewhere here. Let's say 0 is the mean for this case. Now, in terms of variance, it will give us the dispersion, and that is given by the term sigma square, where sigma is the standard deviation, and this would be around the mean in this case. So variance is defined as the spread or the average expected deviation around the mean. Now, if we come to the asymmetrical part, that is given by the skewness, that is the third moment, it would be given by, we first try to shift it by the mean, and then we also divide it by the standard deviation. So we actually are trying to normalize this quantity and then raising it to the power of 3 and then calculating the expectation. So this would actually give us how asymmetric or how the tail is biased towards either of these sides. So if we look into the different shapes, one of the shapes could either be looking something like this, or one of the shapes could either be looking something like this. So this is a positively skewed distribution, and this is a negatively skewed distribution. Similarly, if we look into the kurtosis, that is the tail weight, we can see that it is given by, again, the normalized form, normalized random variable that we subtract by mean and divide by the standard deviation, and we raise it to the power of 4. And this 4 makes the small numbers a lot bigger, and that's why it becomes a bit more sensitive to outliers. This is, again, a relatively zoomed in diagram for this. So the first moment, that is mean, is given by this location. Similarly, variance is given by this spread. Third moment, skewness, where the data is pointing, would be the asymmetric nature of the distribution. And the fourth moment, kurtosis, is how heavy are the tails. In this case, if we see that we can have a distribution something like this, and this is the heaviness of the tail that we can calculate. Now, we notice that variance and kurtosis are both raised to an even degree. They can both be sensitive to outliers. Kurtosis can be more. But let's say how we can distinctly define two distributions if they are having the same variance, let's say equal to 1. So if, for example, we have a normal distribution that is given by this orange curve, a uniform distribution that is given by this blue curve, a Laplace that is given by this green curve, and this yellow curve is the t-distribution that we have. And if you notice, for a normal distribution, we have the kurtosis as 3. Now, we all sometimes consider this as a reference value for kurtosis. Now, if anything that is below 3 is considered to be with a less heavier tail, and something above 3 is considered to be with a relatively heavier tail than a normal Gaussian distribution. And we can notice that from this example itself, that for a uniform distribution, because if you see that it's truncated right here, so there are no outliers after this region, and we can see that it's the kurtosis as compared to the Gaussian is lesser for uniform distribution. And if we see for Laplace, it's more than 3. And for Laplace, if you see, this is the green curve, and it is slightly above this Gaussian curve when we are actually extending it to infinity. And for the case in tree distribution, we can see that this curve is again a little above than the Gaussian and the Laplace distribution. So that tail is a bit heavier than all of these distributions. So we can and the kurtosis is approximately 9 for this. So we can see the kurtosis measures how heavy are the tails. One thing that we missed here is, if you notice the units. So let's say we're dealing with some heights, like with the data distribution related to some height of the people in a city. So the unit for this would be, let's say, meters. Similarly, for variance, the unit would be meter square. But if you notice the values for skewness and kurtosis, because we are normalizing it, we are also dividing it by the standard deviation. This entity would not have any units. Same is the case for kurtosis. So we can see that skewness and kurtosis are actually related to just the shape and the characteristics of a particular distribution. So they can be considered as some score that is given based on the asymmetry of the distribution, or the tail heaviness or the peakedness of the distribution. So they are just some scores, where for normal distribution, the score for kurtosis is just given by 3, and we can see that there are no units in this case. So far what we have covered is the first moment, that is the mean, is where the data stands. The second moment, that is variance, is how the data revolves or how the data is spread around the mean. The third moment, skewness, gives us the inclination or the tilt or the asymmetry of the data around the mean again. And the fourth moment, kurtosis, that gives us the heaviness of the tail. Now, what if all these statistical moments are same? For example, when the data has the same mean, we can have distributions with different variance. Now, if the variance is also the same, we can have distributions with different asymmetry, that is different skewness. But if skewness is also the same, like mean, variance, skewness, all are the same, then we can have a distribution that can probably have maybe heavier or less heavier tails. But what if all these four moments are the same? Then how can we again characterize or differentiate between two different distributions? So these moments are actually used to differentiate between different distributions. So, but what if all of them are same? So then probably we can use some high moment, statistical moment, but there can be some other ways as well. Maybe we can use some distance-based metrics like KL divergence to find the distinct differences between the two distributions, or how much they are different from each other. It's very similar to an example where, let's say, we are comparing two human beings that are same in terms of weight, same in terms of height, same in terms of their shoulder width, and same in terms of their, let's say, waist. Now, if all of these parameters are same, do you think that they are the same people? Might not be. They can be totally different people, and there could be a number of ways to identify other differences that could be there. Same is the case with probability distributions. Most of the time, these statistical moments would be sufficient enough to give good amount of information about the distributions. But if not, then we can resort to some other ways as well. So that's it for this particular video. In the next video, we'll try to break down the formula for variance, like how do we calculate variance given certain data samples. Till then, happy learning. Thanks for watching.